Tonight, we're going to ask a question that sounds simple and turns out to be one of the most difficult problems in physics and sociology combined. How long could a generation ship actually survive in deep space? Not how long in theory. Not how long if everything goes right. How long under realistic conditions, with real human beings, real mechanical systems, real radiation, and real biology? That is the question. And the answer, when you work through it carefully, is far more complicated than either the optimists or the pessimists suggest. Before we get started, if you love exploring the mysteries of deep space as much as we do, take a second to subscribe or like the video. It helps this channel reach more curious minds like yours. Now let's begin. We should start with the distance problem, because it sets the scale for everything else. The nearest star to our Sun is Proxima Centauri, a red dwarf 4.24 light-years away. A light-year is approximately 5.88 trillion miles. Proxima Centauri is therefore about 25 trillion miles from Earth. The fastest spacecraft humanity has ever launched is the Parker Solar Probe, which at its perihelion, its closest point to the Sun, travels at approximately 430,000 miles per hour. At that speed, the journey to Proxima Centauri would take roughly 6,600 years. No one expects a generation ship to use a Parker Solar Probe engine, but the speeds we're talking about for any remotely practical interstellar mission are a small fraction of the speed of light. The most ambitious serious engineering proposals, studies that go beyond speculation to actual design work, typically aim for something between 5% and 12% of the speed of light. At 10% of light speed, the trip to Proxima Centauri would take about 42 years. At 5%, about 85 years. Proxima Centauri is the closest option. A more hospitable destination like TRAPPIST-1, with its 7 planets and 3 in the habitable zone, is 39 light-years away. At 10% of light speed, that is a 390-year journey. At 5%, 780 years. Those numbers, 85 years to 780 years, define the mission duration space that a generation ship would need to survive. Not a generation. Multiple generations. The ship would have to launch with a founding population, and that population would have to maintain not just physical survival, but social coherence, biological diversity, technical knowledge, and a shared mission purpose across periods of time that dwarf any continuous human civilization we have maintained in one enclosed place. We need to be specific about what we mean by survive. A ship that reaches its destination with 10 genetically depleted, psychologically broken survivors who can no longer operate the landing systems has not survived in any useful sense. What we want when we ask how long a generation ship could survive is, under what conditions and for how long could the ship maintain the capacity to complete its mission? That includes maintaining a viable crew population, maintaining the life support systems that keep them alive, maintaining the technical knowledge required to operate and repair those systems, and maintaining the social structures that allow humans to function cooperatively over centuries. Each of those 4 requirements turns out to have its own failure modes, and no one expects all 4 of them to hold for 5 centuries without deliberate, careful design. The question is whether that design is achievable and what its limits are. Let's talk about the distance problem from the perspective of fuel and propulsion first, because it determines everything else about the ship's design constraints. The Tsiolkovsky rocket equation, formulated in 1903 by Konstantin Tsiolkovsky, a Russian schoolteacher who is now recognized as one of the fathers of theoretical rocketics, tells us the relationship between the fuel mass required and the velocity change achievable. In simplified terms, it says that to achieve very high velocities, you need to carry an enormous mass of propellant relative to your payload mass. This is fine for going from Earth to the Moon. It becomes catastrophic when you try to apply it to interstellar distances. If you wanted to use conventional chemical rockets, the highest specific impulse propellant combination we have, liquid hydrogen and liquid oxygen, you would need a fuel mass that is millions of times the mass of your payload just to reach 10% of light speed. No such rocket is buildable. The mass ratio required makes it physically impossible with any chemical propellant. This is why every serious generation ship proposal uses nuclear propulsion of some kind. Nuclear reactions release energies that are millions of times more concentrated than chemical reactions. The British Interplanetary Society's Project Daedalus study, conducted from 1973 to 1978, and involving a team of professional engineers and scientists, proposed a two-stage fusion drive using deuterium and helium-3 as fuel. The study's conclusion was that a vehicle massing approximately 54,000 tons at launch, of which 50,000 tons was fuel, could accelerate a 500-ton payload to 12.2% of light speed. At that velocity, the journey to Barnard's star, 596 light-years away, would take 49 years. The key number to hold on to is the mass fraction. The Daedalus ship was roughly 92% fuel by mass at launch. The entire mission payload, the science instruments, the structural elements, everything that was not fuel, was about 8% of the total mass. That is for an unmanned probe. A crewed ship, which requires life support systems, food production, radiation shielding, crew quarters, medical facilities, and thousands of tons of redundant systems, would be significantly heavier than a 500-ton probe. The mass ratios become correspondingly worse. By the end of tonight, we will understand exactly why those mass ratios matter, what they imply for the systems that would have to survive the journey, and why the engineering problem and the biology problem and the social problem are all connected to each other in ways that make a generation ship one of the hardest problems our species has ever tried to seriously think through. We should take a moment to look at the actual engineering proposals that have been made, because they give concrete shape to what we are discussing. The British Interplanetary Society's Project Daedalus, conducted between 1973 and 1978, was the first serious professional engineering study of an interstellar spacecraft. It was unmanned, designed specifically as a probe rather than a crewed ship, but its conclusions about propulsion and mass ratios set the parameters that subsequent crewed proposals have had to work within. The Daedalus design called for a two-stage inertial confinement fusion drive, igniting pellets of deuterium and helium-3 at a rate of 250 per second, with the plasma exhaust providing thrust. The first stage would run for 2 years, burning through 46,000 tons of fuel. The second stage would run for 2 years more. The result would be a 450-ton payload probe travelling at 12.2% of light speed, reaching Barnard's star in 49 years. The British Interplanetary Society revisited the Daedalus study with Project Icarus beginning in 2009, this time with more modern engineering tools and a mandate to produce an improved design that could be achieved with near-future technology. Icarus ran for several years and produced a series of technical papers. One significant update from Daedalus was that the Icarus team noted the helium-3 supply problem. Helium-3 is extraordinarily rare on Earth, and the Daedalus study proposed mining it from the atmospheres of Jupiter or Saturn using orbital factories, which is a significant engineering project in its own right before the Interstellar mission even begins. Project Orion, conceived in the late 1950s by a group of physicists at General Atomics, including Freeman Dyson, proposed a completely different approach. An Orion spacecraft would be propelled by detonating nuclear bombs behind the ship and riding the blast wave on a pusher plate. The efficiency of this approach is surprisingly good by interstellar standards. Calculations suggested that a large Orion ship, massing thousands of tons, could reach perhaps 3% to 10% of light speed. The main obstacle to Orion was the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space. Orion never progressed beyond theoretical design. For crewed missions specifically, the concept of the world ship represents the larger scale proposal. A world ship articulated in detail by Adrian Mann and others building on work by Daedalus team members would not be a ship trying to be as small and fast as possible, but a vast self-contained habitat capable of supporting a population of thousands, or tens of thousands, for thousands of years. The world ship concept abandons the goal of speed and instead optimizes for sustainability. At very low velocities, perhaps 0.1% of light speed, you need much less propulsive energy, and the longer mission duration, perhaps 10,000 years to reach even Proxima Centauri, gives you time to solve problems that a faster mission would face as acute crises. Whether human social institutions can maintain coherence across 10,000 years is an even more daunting question than the 300-year scenario. The Initiative for Interstellar Studies, a UK-based organisation, has continued academic work on generation ship viability. Their 2014 Starship Congress event brought together researchers working across propulsion, life support, social science, and ethics to address the problem. The consensus from that meeting was that no fundamental physical law prevents a generation ship, but that the technology gaps, particularly in fusion propulsion, closed-loop life support, and long-duration materials, are substantial. The CT Institute researcher Douglas Vercock has pointed out that the social and institutional design challenge may be the hardest of all, because physics and engineering have clear research paths forward, while the question of how to design a society that maintains coherence and purpose across 15 generations has no comparable experimental program. There is one more category of proposal that sidesteps most of the problems we have been discussing: the sleeper ship, or the ship with a largely hibernating crew. If the majority of the crew could be placed in some form of medically induced hibernation for most of the journey, with only a small rotating watch crew kept awake at any given time, the food, water, air, and social problems would all be enormously reduced. The challenges of multi-generational population management and knowledge transmission would largely disappear. The genetic problem would still exist, but could be addressed through stored genetic material rather than managed breeding. The obstacle to the sleeper ship concept is biology. Human metabolic hibernation of the kind required, slowing the body to a stable low-temperature state for decades, does not exist as a technology. Some animals do hibernate, but for months, not decades, and by mechanisms that do not scale to the human metabolic profile. There is active research in therapeutic hypothermia for medical applications, and some researchers believe that a mild hibernation state, reducing metabolism by 30% to 50%, could be achievable for humans within decades. But deep hibernation for years remains speculative. No one has demonstrated it. No one knows the long-term physiological effects, and the failure modes of a ship full of deeply hibernating humans, where no one is capable of responding to a system emergency for months at a time, are severe. Let's talk about population genetics, because it is the constraint that is least intuitive and the one that most seriously affects how we think about generation ship viability. The founding population of a generation ship cannot simply be the number of people you need to operate the ship. It has to be large enough to maintain genetic diversity across the entire mission duration. If it is not, the population will experience genetic drift, the random loss of genetic variance through chance over time, and inbreeding depression, the accumulation of harmful recessive alleles that express themselves when relatives mate. Both of these processes are well understood in conservation biology, where the same problems arise with small and isolated animal populations. The minimum viable population concept in conservation biology was first developed in the 1980s. The original estimates for mammals were surprisingly small, around 50 individuals, but this was for the minimum population to avoid immediate extinction from random demographic variation. A more relevant number for a long-duration mission is the minimum inbreeding-free population, which is substantially larger. Charlie Cameron, a researcher at the Initiative for Interstellar Studies, published a population simulation study in 2018 that modelled what happens to a founding crew population over multi-century missions under different starting sizes and different mating strategies. The results were sobering. A starting crew of 98 people, maintained with careful genetic management and deliberate pairing to avoid close relatives, could technically reach a destination 300 light-years away over a 5,000-year journey with acceptable inbreeding coefficients. But acceptable in this context means a coefficient below 0.1, which is still equivalent to the offspring of first cousins. The margin is not comfortable. More practically relevant simulations, those focused on missions of 300 to 500 years rather than 5,000, and aiming for a TRAPPIST, one rather than far more distant targets, suggest that a minimum founding crew of around 160 people is needed for a 300-year mission with no formal genetic management. A study published by Frederick Marin and Camille Belufi in 2018, running simulations of generation ship demographics with varying crew sizes and mission durations, found that for a 500-year mission to Proxima Centauri, a founding crew of 98 with basic genetic awareness of relatedness could maintain acceptable diversity, but with very little margin for disease, accidents, or social disruption that caused clusters of the population to reproduce less. Their 2020 follow-up study raised the recommended figure substantially when they introduced more realistic models of illness and disaster. The number that appears most often in serious generation ship literature is between 150 and 500 founding individuals. Larger is safer. The floor of 160 assumes no significant attrition events, no ideological splits that cause subgroups to stop interbreeding with the rest of the population, no genetic bottlenecks from catastrophic events that kill disproportionate fractions of the reproductive population, and deliberate active genetic management. None of those assumptions are guaranteed over centuries. What genetic management means in practice is that the ship would need to track the genetic relatedness of every individual and pair individuals for reproduction, or at minimum strongly encourage pairings in ways that maximize genetic diversity rather than reflect natural social choices. This is enormously invasive from a personal autonomy standpoint. It requires that every person on the ship know that their reproductive choices are constrained by genetic registers that have been maintained since the founding generation. It requires that the biological information be accurate and accessible across the entire mission duration, and it requires that the generations born aboard the ship, who had no say in being placed in this situation, accept the constraints as legitimate and necessary. No one expects that to be uncontested. The history of human societies shows that reproductive autonomy is one of the most fiercely defended personal liberties. Enforcing genetic pairing requirements across 15 generations of people who were born into the mission, never asked to join it, and may resent the entire enterprise would require social control mechanisms that raise serious ethical questions about what kind of society you want to arrive at your destination. There is an alternative approach that sidesteps most of these problems, and it involves carrying frozen genetic material rather than a large living population. If the ship carries frozen sperm samples from several thousand donors, carefully selected for genetic diversity, the founding living crew can be substantially smaller, perhaps 30 to 50 people in terms of the actual population aboard the ship. Children can be born using donated sperm to introduce genetic diversity without requiring a large living crew. This dramatically reduces the population size you need to support and the food and resources you need to produce. But it introduces its own complications around who decides whose samples get used, how the reproductive technology is maintained over centuries, and what the social implications are for children who are born from anonymous donors in a context where the entire living population knows each other. There are also proposals involving the cryopreservation of embryos, which would allow a very small operational crew, perhaps 20 to 30 people, to manage the ship, with the majority of the founding population stored as embryos and born progressively over the course of the mission. This is the most resource-efficient approach from a biological standpoint, but it requires the maintenance of cryogenic storage for centuries. It requires functional artificial womb technology, or a small group of biological mothers to carry and bear the embryos, and it requires that the small operational crew successfully raise and educate the progressively born cohorts. The genetic problem, in summary, does not have an easy solution. Every approach involves either a large living crew with all the resources and social complexity that implies, or smaller crews with technological dependencies that have to function flawlessly for centuries. What no one disputes is that a crew that simply boards a ship in whatever numbers are convenient and has children without genetic awareness or planning will face serious biological problems within a few generations. The ethical dimension of the generation ship problem is one that does not have a clean engineering solution, and it is worth sitting with it seriously. The central ethical objection to the generation ship concept was articulated clearly by the philosopher Toby Ord in his work on existential risk and by others working in bioethics. It is this: the founding crew can consent to the mission. They are adults who have been informed of the conditions and the risks, and who have chosen freely to participate. But every person born aboard the ship after the first generation has not consented. They were born into the mission, they did not choose it, and they cannot leave it. This is not a small distinction. The founding generation's children and their children's children will live their entire lives in a bounded metal cylinder in interstellar space, under conditions that their ancestors chose and that they cannot change or exit. The degree of control exercised by the founding generation over the lives of every subsequent generation is almost without parallel in human history. We do not generally consider it ethical to make choices for future generations that they cannot reverse and were not consulted about. The counter-argument is that parents always make choices that constrain their children's lives. Parents choose where to live, in what community, under what cultural and religious framework, in what economic circumstances. Children do not consent to being born in a poor country rather than a wealthy one, or in a religious household rather than a secular one, or in a society at war rather than at peace. The generation ship is arguably just a particularly extreme version of the choices that every human birth involves, but there is a difference in kind as well as degree. A child born in a poor country can emigrate. A child born in a religious household can convert or leave. A child born in a war can become a refugee. None of these options are easy, and none of them are available to everyone, but they exist. A child born on a generation ship in interstellar space cannot leave. The choice made by the founding generation is genuinely irrevocable for every subsequent person. This ethical objection has real practical implications. If the generations born aboard the ship come to feel, strongly and collectively, that the mission is unjust, that they are being forced to sacrifice their lives for a goal they did not choose, they may resist or refuse to maintain the ship, to reproduce, to train their children, or to cooperate with the governance structures. Passive resistance of this kind would be very difficult for any authority structure to counter, because the threat of punishment is constrained by the need to maintain population size and social function. There are some proposed mitigations. One is to design the ship's social structure specifically to give the ship-born generations genuine agency over their own lives within the constraints of the mission. This means designing governance systems in which ship-born individuals have real power to make collective decisions about how the mission proceeds, not just implementing the founding crew's original plan. It means designing the educational system to give people genuine options within the ship's community, not just training them for predefined roles. It means designing the physical environment to provide as rich a social and cultural life as possible. These are not trivial design challenges. A ship with 200 people is smaller than the smallest viable town. The range of careers, relationships, cultural experiences, and social identities available to a person on the ship is inherently more constrained than on Earth. But the degree to which the founding generation designs for this constraint, versus treating the ship purely as a vehicle for getting humans from one star to another, may determine whether the people aboard the ship in generations 8 through 15 feel like participants in a great adventure or inmates of a prison. The SETI Institute's Catherine Denning, who has written extensively on the social science of interstellar travel, has argued that the generation ship concept requires rethinking what we mean by consent across time. She proposes that a generation ship would need something like a constitutional framework that includes explicit provisions for the shipborne generations to revise the mission parameters, potentially including the destination, if a sufficient majority agrees. This would mean that the mission is not fully determined at departure, but evolves through the decisions of successive generations. The risk, from a mission planning standpoint, is that a future generation decides to return to Earth rather than continue. But this risk may be an unavoidable consequence of taking ethics seriously. The alternative, a generation ship that locks in the founding generation's choices irrevocably and designs social control mechanisms to ensure compliance across centuries, is a form of what Denning calls coercive perpetuation. Whether it would succeed is uncertain. Whether it should be attempted is a different question. These ethical issues are not merely philosophical. They have direct practical implications for ship design, governance architecture, population psychology, and mission planning. A generation ship conceived as a purely engineering problem, ignoring the ethical dimensions, would be designed differently and would likely face different failure modes than one that treats the lived experience of the shipborne generations as a primary design constraint. The most thoughtful researchers in this area consistently argue that you cannot solve the social and ethical problems separately from the technical ones. They are part of the same design challenge. Let's talk about what breaks. Any mechanical or electronic system has what engineers call a mean time between failures, the average time between breakdowns of a given component under operational conditions. When you design a mission that lasts 300 years, you're designing around the certainty that virtually every system on the ship will fail many times, and that the ship must be able to repair itself with no external supply chain, no spare parts manufacturing on Earth, and no technical support from the engineers who originally designed the systems. The International Space Station, which is our most sophisticated long-duration crewed space habitat, has been continuously occupied since November 2, 2000. It requires approximately 40 resupply missions per year from Earth. Its crew spends a significant fraction of every week on maintenance and repair. It has experienced thousands of equipment failures over its operational life, ranging from minor sensor malfunctions to serious problems with CO2 scrubbers, oxygen generation systems, and attitude control. Each of those failures was resolved with replacement parts shipped from Earth within days or weeks. The ISS has also been continuously upgraded, with new modules added and outdated systems replaced. The version of the ISS operating today is substantially different from the version that launched in 1998. A generation ship cannot do any of that. It carries everything it will ever have. If a critical component fails and there is no spare and no way to manufacture one, the component fails permanently. The question then becomes, was that component redundant? Was there a backup? And if so, what is the failure rate of the backup? And does the backup have a backup? We can be more precise. Suppose a life support component has a mean time between failures of 10 years, which is reasonable for a high-quality mechanical system. Over a 300-year mission, that component will fail, on average 30 times. If it has one backup, you need both to fail at the same time, which given the failure rate means a window of a few years in a 300-year mission, where the failure of the first is followed by the failure of the second before the first is repaired. That is manageable. But if the failure rate is higher, or if the component has no backup, you have a problem on a timescale shorter than the mission. The components most subject to this analysis are the ones that cannot fail without killing the crew. Atmosphere management, specifically oxygen generation, and carbon dioxide removal is the most critical. Water recycling is second. Thermal regulation, the system that keeps the ship from becoming either an oven or a freezer, as it moves through interstellar space far from any star, is third. Food production, if the ship grows its own food, is fourth. Power generation, which underlies all of the above, is fifth. Each of these systems has what engineers call single points of failure, components that, if they break without a backup, cause the entire system to fail. Identifying and eliminating single points of failure through redundancy is standard engineering practice, but complete redundancy of every component is not achievable in practice, because it doubles the mass and complexity of every system, and mass is the most limited resource on an interstellar ship. The situation becomes more complicated when you consider that the people aboard the ship after the first generation may not fully understand the systems they are responsible for maintaining. The founding crew would have been trained engineers and technicians, but training does not automatically transfer across generations. A child born on a generation ship can be taught how to perform routine maintenance on the oxygen system. Whether that child fully understands the underlying engineering well enough to diagnose an unfamiliar failure mode and improvise a repair is a different question. Engineering knowledge, like all knowledge, requires active transmission, active practice, and a culture that values and rewards it. Over generations, there is a real risk of what researchers call a knowledge fade, a gradual erosion of technical understanding as the tacit knowledge held by practitioners is not fully transmitted to the next generation. This is not hypothetical. We have historical examples of technological regression in isolated communities. The Rapa Nui of Easter Island lost the ability to build seaworthy ocean-going vessels after they were isolated on the island for centuries. Medieval European metalworkers lost the ability to produce Roman-quality concrete and some grades of Roman-quality steel, techniques that had to be rediscovered much later. These are examples from large, stable agricultural societies. A generation ship crew of a few hundred people under constant physical and psychological stress is not a more favourable environment for knowledge preservation. By the end of tonight, we will understand exactly how these technical failure modes interact with the social and biological problems we have been describing, and why the generation ship problem is not just an engineering problem, or just a social problem, but both simultaneously, requiring solutions in all domains at once. The life support problem for a generation ship is really three overlapping problems: closing the oxygen-carbon dioxide loop, closing the water loop, and closing the food loop. Each has been studied extensively. None has been fully solved at the scale required. The oxygen-carbon dioxide problem is the most urgent, because humans produce CO2 with every breath and require a continuous supply of oxygen. A crew of 200 people exhales approximately 8 kilograms of CO2 per hour and requires approximately 6 kilograms of oxygen per hour. On the ISS, both of these are handled by active chemical systems. The oxygen generation system uses electrolysis to split water into hydrogen and oxygen, producing breathable O2. The carbon dioxide removal assembly uses zeolite molecular sieve materials to absorb CO2 from the cabin atmosphere. The CO2 is then processed by the Sabatier reactor, which combines it with hydrogen to produce water and methane, with the water fed back to electrolysis and the methane vented to space. This system works, but it is not closed in the relevant sense. The methane is vented, which means carbon is lost from the system and must eventually be replaced. The water used for electrolysis must be continuously supplied, and the zeolite sorbents in the CO2 removal system degrade over time and must be replaced. On the ISS, all replacements come from Earth. The Melissa project, running since 1989 under ESA, aims to close the loop by using a series of biological reactors to process waste streams. In the Melissa design, organic waste from crew and from inedible plant material is fed into a thermophilic bacterial compartment that breaks it down into simpler molecules. These molecules feed into a photosynthetic bacterial compartment that further processes them and produces organic compounds. A nitrifying bacterial compartment converts ammonium to nitrates, and a plant and algae compartment, using artificial light and the nitrates from the nitrifying stage, produces food and oxygen while consuming CO2. The Melissa project has successfully demonstrated each compartment individually and has run small-scale integrated tests. In 2009, they achieved a genuine closed loop for mice for a period of weeks. Scaling to humans remains the challenge. The plant compartment requires grow lights that consume substantial power, and the biological systems are sensitive to contamination, pH shifts, and the specific nutrient balance coming from upstream compartments. The overall system is complex enough that running it for centuries without skilled biological intervention may not be feasible. A simpler and more robust alternative for oxygen production is a large planted area. Wheat, soybeans, potatoes, and sweet potatoes are all photosynthetically efficient crops that produce substantial oxygen as a byproduct of growth, and that also produce edible food. A planted area of roughly 50 square meters per crew member, or 10,000 square meters for 200 crew, has been calculated to be sufficient for both oxygen production and partial food supply, depending on crop selection. This is approximately equal to the floor area of a reasonably large warehouse. Not an impossible volume for a ship designed from the outset to accommodate it. But 10,000 square meters of growing area under artificial light represents a significant fraction of the ship's total volume and a major continuous power draw. Growing lights for crops in space typically consume roughly 200 to 400 watts per square meter of growing area, so 10,000 square meters would require 2 to 4 megawatts of growing light power continuously across the entire mission duration. The water loop is somewhat easier to close than the oxygen and food loops, at least in principle. The ISS currently recycles approximately 90% of its water, recovering moisture from the atmosphere and from urine through the water recovery system. This has been functioning since 2008 and has been progressively improved. The main loss mechanisms are water vapor leaking from airlocks and water incorporated into solid waste that cannot be economically recovered. A generation ship would aim for a high recovery percentage, perhaps 98% to 99%, which would require very small replenishment from whatever ice sources might be available in the interstellar medium, or from a large initial stock. The food problem is the most biological and therefore the most complex, not just in terms of growing area and power, but in terms of agricultural knowledge, crop diversity, soil microbiology, plant disease management, and seed viability over centuries. A closed agricultural system is an ecological system, and ecological systems have dynamics that are difficult to predict and control. Plant diseases evolve. Pest organisms, even in a sealed spacecraft, can evolve from the microbial and invertebrate communities that inevitably colonize any biological system. The nutritional profile of food grown in a closed system over centuries may shift in ways that create subtle deficiencies. Vitamin D synthesis, for example, requires ultraviolet light that is not naturally present inside a spacecraft, and must be supplied either through dietary supplements of indefinite supply or through specialized lighting. The Soviet BIOS-3 experiment, conducted in Krasnoyarsk from 1972 to 1984, placed crews of 2 to 3 people in a closed habitat of 315 cubic meters for periods of up to 6 months. BIOS-3 achieved partial closure of the food loop, with participants obtaining roughly 70% to 80% of their calories from plants grown within the habitat. This was the most successful closed life support experiment ever conducted in terms of food production percentage. The crew reported high levels of stress from the monotony of the diet and the intensity of the agricultural labor, which occupied several hours per crew member per day. The system was not fully closed and required external resupply for some nutrients. What BIOS-3 demonstrated is that closed life support is possible, at least partially and at short timescales. What it did not demonstrate is that it can be maintained at high reliability over centuries with an ever-changing crew, or that the biological systems remain stable over the long term without external intervention. Let's talk about power and food, because these are the physical foundations that everything else rests on. A generation ship needs a power source that can function for centuries without refueling. In interstellar space, solar panels are useless because the solar flux at 1 light-year from the Sun is approximately 15 billion times weaker than at Earth. The ship is entirely on its own for energy. The most mature technology available for long-duration space power is nuclear fission. Fission reactors have been used in space since the 1960s, though only in small research and military satellites in low Earth orbit and briefly on some Soviet spacecraft. The physics is well understood. Fission reactors can produce continuous power for decades with a single fuel load. The main limitations are the amount of fissile material required for long operation, the degradation of reactor components under radiation flux, and the eventual depletion of the fuel. A fission reactor sized to power a generation ship, providing tens of megawatts continuously for electricity and thermal management, would consume fissile uranium or plutonium at a rate that, over 300 years, would require carrying a very large initial fuel load or having a breeding cycle that produces new fissile material from non-fissile feedstock. Breeder reactors, which produce more fissile material than they consume by converting fertile uranium-238 or thorium-232 into fissile plutonium-239 or uranium-233, are a possible solution but are technically complex and have been largely abandoned in terrestrial programs due to safety concerns, proliferation worries, and cost. The practical alternative is nuclear fusion, which uses hydrogen isotopes as fuel and produces helium as waste, with a fuel supply that, in principle, can be sourced from interstellar hydrogen or from a large initial stock. The problem is that controlled nuclear fusion for power generation has been actively researched for 70 years and remains not commercially viable as of today. The ITER reactor under construction in France is expected to demonstrate net fusion energy gain in the early 2030s, but demonstrating net gain in a laboratory setting is different from producing a compact, robust, self-sustaining fusion power plant that can operate without maintenance for 300 years aboard a spacecraft. The food problem is, if anything, more tractable than the power problem, but still formidable. A crew of 200 people needs approximately 600 to 800 kilograms of dry food per day, or roughly 200 to 300 tons per year. Carrying 300 years of food is obviously impossible. The ship must grow its own. Closed-loop food production in space is an active research area. NASA's Advanced Life Support Program and ESA's MELISSA project, which stands for Micro-Ecological Life Support System Alternative, have both conducted extensive research into what it would take to grow food in a closed system in space. The MELISSA project, which began in 1989 and is still running, aims to design a closed ecological system that can recycle all waste products, human and biological, back into food and clean water with no external input. The results from MELISSA and related programs are encouraging but incomplete. Closing the carbon and nitrogen loops in a small system is achievable in principle, and partial closure has been demonstrated experimentally. But a fully closed system that can sustain humans indefinitely, with no external inputs, operating at the scale required for 200 people, has not been demonstrated. The Biosphere 2 project in Arizona, a much publicized attempt to create a fully closed ecological system, large enough for 8 people for 2 years from 1991 to 1993, failed to maintain atmospheric oxygen levels and required external oxygen injection halfway through the first mission. The CO2 scrubbing was performed partly by concrete absorbing CO2 from the atmosphere, a process the designers had not anticipated and which reduced atmospheric oxygen below comfortable levels. These failures are instructive but not fatal to the concept. The Biosphere 2 team was under-resourced and working with 1990s technology in a system that was deliberately oversized for its crew. Modern understanding of closed ecological systems is substantially better. But the point stands that we have never successfully closed the loop on a life support system at the scale required for a generation ship. The crop system also has to be robust against the failure of individual species. A ship that grows only a small number of crop varieties is vulnerable to the collapse of any one variety from disease, genetic depletion, or system failure. Maintaining genuine crop diversity across the mission duration requires storing seeds for many varieties, managing their viability over centuries, and having the agricultural knowledge to cultivate them. Seed viability decreases over time even under good storage conditions, though very low temperatures, approaching but not at cryogenic levels, can extend viability considerably. A ship's agricultural diversity depends on the long-term integrity of seed storage systems that operate continuously for the entire mission duration. The power and food problems are solvable in principle, but they require technologies that are more mature than what we currently have, and they require those technologies to work reliably for timescales longer than any technology we have ever built has operated. The oldest continuously operating mechanical device on Earth is probably the Dover bronze bell, cast in the 13th century and still rung at intervals, though it is not a machine in the relevant sense. The oldest continuously operating power plants are less than 150 years old. We are asking a generation ship systems to operate for twice that duration, without refueling, without external maintenance support, and without the possibility of replacement. Propulsion is the foundational problem of interstellar travel. Everything else about a generation ship, the size, the mass, the mission duration, the destination, flows from the question of how fast a ship can go and how much it costs in mass and energy to go that fast. The first thing to understand is why chemical rockets, which have gotten every human and every spacecraft off Earth's surface, are fundamentally unable to reach the speeds required for interstellar travel. The exhaust velocity of the best chemical rockets, liquid hydrogen burning in liquid oxygen, is approximately 2.7 miles per second. The Tsiolkovsky rocket equation tells us that the ratio of propellant mass to payload mass needed to reach a given velocity scaled exponentially with the ratio of that velocity to the exhaust velocity. To reach 10% of the speed of light, approximately 18,600 miles per second, from an exhaust velocity of 2.7 miles per second, you would need a mass ratio of e to the power of 6,118. This is a number with nearly 3,000 digits. It is not merely impractical. It is so far beyond impractical that the entire observable universe does not contain enough matter to fuel such a rocket. The only escape from the tyranny of the rocket equation is to increase the exhaust velocity. Nuclear thermal rockets, where a nuclear reactor heats a propellant rather than a chemical reaction, can achieve exhaust velocities of roughly 5 to 6 miles per second. This is better than chemical rockets, but still far too slow to make interstellar travel in human timescales possible. The mass ratios required are still astronomical. Nuclear pulse propulsion, the Orion concept, represents a much more dramatic improvement. By detonating nuclear bombs and riding the blast wave on a massive pusher plate, Orion designs can theoretically achieve exhaust velocities of around 620 to 6,200 miles per second, depending on the design specifics. At the high end, this is 3% of light speed, which would get a ship to Proxima Centauri in about 140 years. The basic physics is sound. The nuclear weapons required are in principle buildable. The main obstacle is the Test Ban Treaty and the political reality of launching nuclear weapons from Earth's surface. An Orion ship would need to detonate thousands of nuclear bombs in a launch sequence from Earth orbit or beyond. Fusion propulsion, as in the Daedalus design, offers exhaust velocities of around 6,200 miles per second, or roughly 3% of light speed for the exhaust products. A two-stage fusion ship can potentially reach 10% to 15% of light speed with a mass fraction of perhaps 90% fuel. The obstacle is controlled fusion itself. Inertial confinement fusion, the specific type proposed in Daedalus, uses lasers or particle beams to rapidly compress and heat small pellets of fuel to fusion conditions. It works in principle. It has worked in laboratories, notably at the National Ignition Facility, which achieved ignition, net energy gain from fusion, in December 2022 for the first time. But ignition in a controlled laboratory setting with multi-billion-dollar laser systems is a long way from a compact, self-sustaining, highly efficient engine that can operate for 2 to 4 years in space. Antimatter propulsion offers the highest theoretical efficiency. The annihilation of matter and antimatter converts 100% of mass to energy, compared to 0.7% for fusion and far less for fission. An antimatter rocket with a mass ratio of just a few would be able to reach a significant fraction of light speed. The obstacles are production and storage. Current antimatter production rates at the world's most powerful particle accelerators produce nanograms per year at a cost measured in billions of dollars per gram. The Daedalus ship needed 50,000 tons of fuel. The antimatter requirement for an equivalent mission would be far less due to the higher efficiency, but even a few kilograms of antimatter, enough to make a meaningful difference to a small probe, is centuries of current production at current costs. Antimatter storage is also unsolved. Antiparticles must be kept suspended in magnetic traps without touching ordinary matter, and the trap must operate perfectly, indefinitely. A failure of the trap releases an annihilation event. The most potentially near-term approach to very high speed is laser sail propulsion, the principle behind the Breakthrough Starshot initiative announced in 2016 by Yuri Milner and Stephen Hawking. The idea is to use a powerful ground-based or space-based laser array to accelerate a very light sail to 20% of light speed. The sail itself, made of ultra-thin reflective material, has no propellant. All the energy comes from the laser. For very small masses, gram-scale probes, the acceleration can be achieved in minutes. For a crewed ship, the mass is many orders of magnitude larger. The laser power required scales proportionally, and the problem of decelerating at the destination becomes acute because there is no laser at the destination to slow the ship down. Breakthrough Starshot is, as currently conceived, a one-way probe concept for extremely small and lightweight instruments, not a crewed mission architecture. The realistic propulsion options for a crewed generation ship are therefore nuclear pulse propulsion and fusion, both of which require technology and fuel that do not exist at scale. The timescale for these technologies to mature is unclear. Some researchers believe fusion propulsion could be achievable within 50 years. Others are more skeptical. What is clear is that no crewed interstellar mission is possible with currently available propulsion technology. The choice of propulsion system also determines the mass budget available for everything else. A more efficient propulsion system allows more mass for life support, radiation shielding, and redundant systems. A less efficient system leaves less. The propulsion and life support problems are therefore coupled. Improvements in propulsion directly translate to more margin for biological and social engineering. Let's talk about radiation, because it is one of the hardest physical problems a generation ship faces, and the one that most directly challenges the assumption that you can simply build a big enough ship and fill it with enough people. There are two distinct radiation environments that a generation ship would need to survive. The first is solar particle events, energetic protons and heavier ions ejected by the sun during flares and coronal mass ejections. These are intense but relatively short duration events, lasting hours to a few days, and they are largely a problem in the inner solar system and near our sun. Within a few years of departure at interstellar speeds, the ship would be far enough from the sun that solar particle events are no longer significant. The second is galactic cosmic rays, and these are the permanent problem that does not go away. Galactic cosmic rays are high-energy particles, primarily protons and heavier nuclei, that arrive from outside the solar system from all directions at nearly constant flux. They are produced by supernovae, pulsar wind nebulae, and possibly other high-energy astrophysical processes distributed across the galaxy. They have energies ranging from tens of millions of electron volts to above 10 to the power of 20 electron volts for the most energetic events, the so-called ultra-high energy cosmic rays. The most important range for biology is the intermediate energy cosmic rays, those above a few hundred million electron volts, because these are the ones that easily penetrate conventional shielding. On Earth, we are protected from most cosmic ray flux by the planet's magnetic field, which deflects charged particles, and by the atmosphere, which is approximately equivalent to 10 meters of water as a radiation shield. On the ISS, which is in low Earth orbit within the magnetosphere, the crew receives about 1 millisievert per day, or roughly 365 millisieverts per year. The career dose limit for NASA astronauts is set at levels estimated to increase cancer risk by no more than 3%. A 6-month ISS mission currently sits near the boundary of acceptable lifetime dose for many crew members. In interplanetary space, outside the magnetosphere but still within the heliosphere, the dose is higher, roughly 1 to 2 millisieverts per day. Over a 300-day mission to Mars, this is manageable. Over a 300-year mission to another star, it is lethal many times over without shielding. Water is one of the most effective passive radiation shields available because hydrogen atoms in water are good at scattering and slowing incoming protons. The problem is the mass. To reduce galactic cosmic ray doses to something approximating Earth surface levels in interstellar space would require a water shield of approximately 20 to 30 meters in all directions around the habitation area. For a habitation module with 200 people, this means hundreds of thousands of tons of shielding water. The mass penalty is extreme. No one expects a practical generation ship to achieve Earth's surface radiation levels. What the engineering trade-off comes down to is how much radiation exposure per year is acceptable across a lifetime, and how much shielding you can afford to carry. Current estimates suggest that a few meters of water-equivalent shielding reduces doses to roughly 100 to 200 millisieverts per year in the galactic environment, which is substantially above current occupational limits for radiation workers, but substantially below acute lethal doses. Over a lifetime of 70 years, this corresponds to cumulative doses of 7 to 14 sieverts, which is associated with significantly elevated cancer risk, but is not incompatible with a normal lifespan for most individuals. The more serious problem may not be cancer, but neurological effects. Studies on Apollo astronauts, who spent brief periods outside the magnetosphere during transit to the Moon, have shown higher rates of cardiovascular disease and potentially cognitive decline compared to low Earth orbit astronauts. Mouse studies at Brookhaven National Laboratory have shown that simulated galactic cosmic ray exposure causes measurable disruption to brain function, specifically to the hippocampus, the region involved in memory formation and spatial navigation, at doses relevant to long-duration spaceflight. If these effects translate to humans on century-long timescales, the cognitive capacity of the crew may degrade progressively over the mission, which would be catastrophic for the technical knowledge maintenance problem we described earlier. The interaction of radiation with genetics is a separate concern. Galactic cosmic rays cause DNA double-strand breaks, which are repaired by the cell's DNA repair machinery, but with imperfect fidelity, introducing mutations at a rate that increases with dose. Over multiple generations, elevated mutation rates can affect the genetic health of the population in ways that compound with the genetic drift and inbreeding problems we have already discussed. The biology and the physics are not independent problems. There is an active area of research into magnetic shielding, which would deflect charge particles using a strong magnetic field around the ship, rather than a passive mass shield. This would be much lighter than water shielding and potentially more effective. But the engineering challenges are substantial. The field strength required would need to be thousands of times the strength of Earth's magnetic field, maintained continuously for centuries using superconducting electromagnets. Superconductors require cooling to within a few degrees of absolute zero. The cryogenic cooling systems required are themselves complex, power-hungry, and subject to failure. No one has built anything like this. It remains a theoretical proposal. Radiation is one of the problems where the solution, if it exists, is fundamentally tied to technology we do not yet have. With current technology, a generation ship crew would receive radiation doses significantly above what we currently consider safe for terrestrial radiation workers. The long-term consequences of those doses over centuries of exposure and multiple generations are not fully understood. There is a physical hazard to generation ships that does not get enough attention in popular discussions: the interstellar medium itself. Interstellar space is not empty. It is filled with gas at very low density, approximately 1 atom per cubic centimetre on average in the galactic disk, and with microscopic dust grains at an even lower density. At the scale of distances we're discussing, these particles are essentially zero obstacles, but at the speeds required for interstellar travel, even individual atoms and dust grains become significant hazards. Consider a ship traveling at 10% of light speed, approximately 18,600 miles per second. A single hydrogen atom encountered at that relative velocity has a kinetic energy, in the ship's reference frame, equivalent to a high-energy cosmic ray. Not lethal at the rate of one atom at a time, but the interstellar medium delivers roughly 1 atom per cubic centimetre, and a ship moving at 0.1 c sweeps a volume of space equal to its cross-sectional area times its velocity times time. For a ship with a cross-sectional area of, say, 1,000 square metres, travelling at 0.1 c, it sweeps approximately 5 billion cubic metres of interstellar medium per second. That is 5 trillion atoms per second striking the forward surface of the ship. At these densities, the cumulative effect is significant over decades. The forward heat shield, or erosion shield, would experience continuous particle bombardment that gradually ablates the shielding material away. The rate depends on the density of the interstellar medium along the specific path travelled, which varies depending on whether the ship passes through denser molecular cloud regions or emptier space. The average density in the galactic disk is well characterised, but the variance is large. A ship unlucky enough to pass through a particularly dense region of the interstellar medium at 10% of light speed could face erosion rates significantly higher than the average. Dust grains are more dangerous. The interstellar medium contains dust particles at a density of approximately 1 grain per million cubic meters, which sounds sparse until you realize that a grain just a micrometer in diameter, traveling at 18,600 miles per second in the ship's frame, carries a kinetic energy equivalent to a small explosive charge. A grain 10 micrometers in diameter, which is well within the normal dust size distribution, would have the kinetic energy of a high-velocity rifle round. The standard engineering response to this problem is a Whipple shield, a spaced armor system consisting of multiple thin layers of material that are designed to vaporize and disperse a high-velocity impactor before it can penetrate the inner wall. This is the same principle used to protect the ISS from micrometeorite impacts. But Whipple shields that are effective against ISS-level micrometeorite impacts, which occur at velocities of roughly 7 to 27 miles per second, need to be substantially more robust to handle the 18,600 miles per second relative velocities of the interstellar medium. The calculation of shield mass required for a given erosion tolerance over a given mission duration is one of the serious engineering design challenges for any high-speed interstellar mission. Models by researchers including Anthony Martin and Alan Bond of the British Interplanetary Society suggest that the forward erosion shield for a Daedalus-type mission would need to be several centimetres of beryllium or similar material and would be significantly eroded by the end of the mission. For a generation ship travelling for 300 years, even at lower speeds, the forward shield mass budget is a significant design constraint. There is also the question of navigation. A generation ship travelling at 10% of light speed in a straight line cannot stop, cannot easily manoeuvre, and cannot afford to encounter even a small solid body in its path. The interplanetary and interstellar space along any trajectory contains comets, asteroids, and planetesimals that are not all catalogued from Earth observations. A collision with a body even a centimetre in diameter at interstellar speeds would be catastrophic. The ship would need some form of detection and deflection system operating continuously across the entire mission duration. Laser ablation is one proposed deflection method, using a powerful forward-pointing laser to vaporize small particles in the ship's path before they can cause damage. This requires continuous high-power laser operation, which requires continuous power and a detection system sensitive enough to find dangerous particles far enough ahead to deflect them at the ship's closing velocity. The engineering is daunting but not impossible in principle. What it adds to the ship is another major power load, another major system requiring continuous operation, and another potential point of failure. The interstellar medium problem is, ultimately, a manageable one for any serious engineering design. It is not a showstopper. but it adds mass, power consumption and complexity to the ship that all compete with the life support, propulsion, and crew systems for the finite resources the ship can carry. Tonight, we're going to talk about something that engineering disciplines call materials degradation, because it is one of the most quietly serious obstacles to a generation ship that receives the least public attention. Everything is made of something, and everything eventually breaks down. The question is how fast. On Earth, we manage materials degradation through a combination of monitoring, maintenance, replacement, and the physical infrastructure that allows us to manufacture new components when old ones wear out. A generation ship has none of that external manufacturing infrastructure. What it departs with is what it has, and materials degrade. Let's be specific about the mechanisms. Metals in space are subject to radiation damage. When high-energy particles, cosmic rays, and energetic photons pass through a metal, they knock atoms out of their positions in the crystal lattice, creating what material scientists call vacancy, interstitial pairs, or Frenkel defects. At high enough doses, this radiation-induced damage causes metal embrittlement, a reduction in the ability of the metal to deform plastically before fracturing. Steel and aluminum alloys that were ductile at mission start may become significantly more brittle after centuries of galactic cosmic ray bombardment. Structural members that were designed to flex slightly under load may fracture instead. The failure mode for embrittled metals is characteristically sudden and catastrophic rather than gradual. The radiation dose required to produce significant embrittlement in steel is roughly 1 to 10 displacements per atom, a measure of cumulative radiation damage depending on the alloy composition and temperature. For a ship in the galactic cosmic ray environment, the time to reach this level of structural damage in unshielded exterior components is measured in decades to centuries, depending on the specific cosmic ray flux along the ship's path and the exact materials used. Polymers, which are used extensively in insulation, seals, gaskets, tubing, electrical wire coatings, and structural composites, are significantly more radiation sensitive than metals. Polymer chains are broken by radiation dose at rates that depend on the specific polymer. Polyethylene, polyamide, and silicone rubber all show significant property changes at radiation doses that could be accumulated over decades in the interstellar environment. Seals and gaskets that maintain pressure boundaries in life support systems may lose their elastic properties over a century. Wire insulation may become brittle and crack. The mechanical and chemical properties of composite materials, which are used in structural applications because of their high strength-to-weight ratio, may degrade in ways that are not immediately obvious from visual inspection, but that reduce the factor of safety against failure. Electronic components have a separate set of degradation mechanisms. Semiconductor devices, which include essentially all modern computing and control systems, fail through a combination of radiation-induced bit flips, threshold voltage shifts, total ionizing dose effects, and single-event upsets caused by individual energetic particles passing through sensitive transistor regions. Radiation-hardened electronics have been developed for space applications, specifically to resist these effects, but hardened electronics require continuous improvement because radiation damage mechanisms are complex, and the hardening techniques that work well against one damage mode may not address another. By the end of tonight, we will understand that the materials problem is not a single engineering challenge, but a spectrum of degradation mechanisms, each with its own rate and failure mode, all operating simultaneously over centuries on every component of the ship. What matters is whether the design includes sufficient redundancy and repairability to absorb these failures, one by one, without any single failure cascade reaching a critical system. There is also a class of materials problem that is specific to the closed environment of a generation ship: outgassing and contamination. Many materials, including plastics, adhesives, and coatings, slowly release volatile compounds into the surrounding atmosphere over time. On Earth, this is managed by ventilation. In a closed habitat, these compounds accumulate. Some are toxic, Some react with other compounds in the air to form new toxic or corrosive products. Some deposit on optical surfaces, reducing the effectiveness of solar panels or imaging systems. The management of atmospheric chemistry in a long-duration closed habitat is a significant materials engineering problem that requires continuous monitoring and active filtration. The maintenance implications of all of this are serious. A generation ship must be able to inspect its structural members for radiation-induced embrittlement, replace its seals and gaskets before they fail catastrophically, maintain its electronic systems against progressive radiation damage, and manage the atmospheric chemistry of its closed habitation volume. Each of these tasks requires specialized knowledge, specialized instruments, and in many cases spare parts or raw materials to fabricate replacements. The concept of in situ resource utilization, which is the practice of using materials available at the destination to produce what you need, rather than carrying everything from home, cannot help a generation ship during transit. The ship is in interstellar space, surrounded by nothing but trace quantities of hydrogen and helium. If a critical structural component needs replacement, the ship must either have carried a spare from the beginning, have the manufacturing capability to produce one from stored raw material, or find some other solution. Manufacturing capability of a meaningful kind is one of the proposals that appears in serious generation ship design discussions. A ship that carries small-scale manufacturing equipment, the space equivalent of a machine shop, could in principle produce replacement components from stored raw materials for many decades. Modern additive manufacturing, which can produce complex metal parts through selective laser sintering or electron beam melting, could be adapted for space use and would dramatically extend the range of components the ship could replace. But additive manufacturing equipment itself requires maintenance. The laser or electron beam source degrades. The powder feedstock for metal printing is limited and cannot be indefinitely replenished in transit, and the manufacturing processes for critical components require quality verification that is itself an engineering challenge. No one expects materials engineering to provide a complete solution to the century-duration maintenance problem. What it can provide is a more complete picture of the failure modes, and therefore a more complete basis for designing around them. The generation ship must be engineered not just for launch conditions, but for the degraded state it will be in after 100 years, after 200 years, after 300 years. Every component that is expected to survive the full mission duration must be designed with the century timescale failure modes in mind. Every component that cannot survive the full mission must have a replacement strategy that is feasible with the ship's manufacturing capabilities and spare parts inventory. This systems-level thinking about long-duration degradation is one of the areas where generation ship engineering is most different from the engineering of conventional space systems, which are typically designed for mission durations of 5 to 20 years. The engineering culture, testing protocols, and design verification methods for 300-year duration systems do not currently exist. Developing them would be one of the first practical engineering tasks of a generation ship development program. The knowledge transmission problem deserves its own careful treatment, because it sits at the intersection of the technical and the social in a way that makes it particularly difficult to solve. A generation ship departs with a crew that has been specifically trained for the mission. These individuals know how to operate the propulsion system, maintain the life support systems, manage agricultural production, provide medical care, navigate the ship, and resolve disputes under the ship's governance structure. They carry this knowledge in their heads and in their hands, the practical knowing that comes from years of training and experience. They also carry it in digital archives, technical manuals, video libraries, and databases. The question is, what happens to that knowledge over 15 generations? The digital knowledge problem sounds easy and is not. We tend to think of digital information as infinitely durable, but data storage media have lifespans that are short compared to interstellar mission durations. Hard drives have a lifespan of roughly 3 to 10 years under continuous use. Solid-state drives degrade from radiation-induced bit flips, which are a particularly acute problem in the cosmic ray environment outside the heliosphere. Optical media like DVDs and CDs can last several decades under ideal conditions but are still subject to physical degradation. Even assuming perfect storage technology, the systems required to read the stored information, the computers, the displays, the interfaces, are themselves mechanical systems with mean times between failures. More fundamentally, information that no one reads is not knowledge. A digital library is only as useful as the ability of the current generation to navigate it, interpret it, and apply it. Technical documentation written for 21st century engineers will be accessible to the first and second generations aboard the ship. But as language, culture, and technical background evolve over centuries, the documentation may become progressively harder to interpret correctly. This is not a hypothetical concern. We have technical documents from the mid-20th century that require specialist historians to interpret correctly today, not because they are damaged, but because the assumptions, conventions, and contextual knowledge they take for granted are no longer universally held. The solution to this problem, the one most often proposed, is apprenticeship. Every critical technical system on the ship should have dedicated specialist crews who train their replacements in person, from the time those replacements are children, emphasizing hands-on practical knowledge in addition to theoretical understanding. A ship's population of 200 might dedicate 20 people to life support, 20 to power systems, 10 to propulsion monitoring, 10 to navigation, 10 to medical, 10 to agriculture management, and so on, each group maintaining its lineage of practical expertise through direct transmission. This works reasonably well for the first few generations, when the founding crew's direct students are still alive and the knowledge has not yet had time to drift. But across 15 generations, the knowledge transmission faces several risks. The first is what we might call lineage fracture. If a specialist lineage loses its only practitioners to a disease, an accident, or a failure of the ship's social system to value the specialization, the knowledge can be lost entirely. A life support system maintained by engineers who do not fully understand its fundamental principles is a life support system that will fail unpredictably when it encounters a novel failure mode. The second risk is cargo cult knowledge, a term borrowed from the anthropological phenomenon of Pacific Islanders who performed the rituals of airstrip construction after World War II in hopes of attracting cargo planes. Having observed the correlation between airstrip building and cargo delivery, without understanding the underlying mechanism. Engineers who know the procedures for maintaining a system without understanding why the procedures work can execute them perfectly as long as the system behaves normally. But if the system behaves abnormally, as all systems eventually do, they cannot diagnose it or adapt. The third risk is cultural drift in values. If the culture of the ship across generations comes to value other things more than engineering competence and technical knowledge, the individuals with the higher social status will not be the engineers and doctors and agricultural specialists. They will be whatever the culture comes to admire, and the apprenticeship system, which requires that technically capable people choose technically demanding careers, will break down. We have seen all three of these patterns in historical isolated communities. The history of Easter Island includes periods in which the specialized knowledge of ocean navigation was lost, probably due to a combination of population stress and social reorganization that reduced the status and transmission of that specialist knowledge. The Norse colonies in Greenland, which lasted from roughly 985 to 1450 CE, ultimately collapsed, partly because the Norse settlers refused to adopt the Inuit adaptations to extreme cold that would have allowed them to survive, maintaining cultural practices that were appropriate in Norway but not in Greenland, even as conditions deteriorated. There is active research into institutional design for long-duration missions. Shannon Silberg and others working in the field of astrosociology have proposed what are sometimes called epistemic institutions, ship-level organizations specifically tasked with knowledge preservation and transmission, with social status and material incentives structured to make knowledge preservation a high-status activity. These could include something like a guild system, in which technical specialties carry formal social recognition, and apprenticeship is a prestigious path, or something like a monastic system, in which certain knowledge traditions are maintained by dedicated groups with strong internal culture regardless of broader social change. What none of these proposals can guarantee is that they will work across 15 generations in an environment that is under chronic physical and psychological stress. We design institutions on Earth for nations of millions or billions of people, with wide population bases to draw practitioners from, with competitive incentives, with external cultural contact that reinvigorates local cultures, and with the constant selective pressure of consequences for failure. A generation ship has none of those features. No one anticipates that knowledge transmission is an easy design problem. What the research community agrees on is that it requires active, deliberate, institutionalized effort from the beginning of the mission, and that passive approaches such as relying on digital archives and hoping for the best are not adequate. Let's talk about the social problem because it may be the hardest one of all. The people who volunteer to board a generation ship would do so knowing they were choosing to leave Earth forever and to spend their lives in transit. They would be motivated individuals with a shared purpose. But their children would not make that choice. Their grandchildren would not make that choice. By the 4th and 5th generations, the people aboard the ship would be individuals who were born into a situation they could not exit, pursuing a mission whose purpose was established before their birth by people they never knew in service of a destination they would never reach. This is not a small psychological problem. It is one of the central ethical objections to the generation ship concept, and it has no clear solution. Sociology and psychology give us some relevant data from isolated human communities. The most instructive case studies are island populations, communities of humans who have been isolated in a bounded physical environment for extended periods. Pitcairn Island, settled in 1790 by the Bounty mutineers and their Tahitian companions, reached a maximum population of about 250 people before declining to fewer than 50 today. Its history includes factional violence, murder, social fragmentation, and periods in which the community appeared to be on the verge of collapse. And Pitcairn is a real island with a functioning ecology, a natural environment, visible sky, and the possibility of departure by boat, however remote. A generation ship is more closed than Pitcairn. There is no ecology, there is no natural environment, there is no sky, and there is absolutely no possibility of departure. The people aboard are committed whether they were consulted about that commitment or not. The sociological literature on closed communities consistently identifies several patterns that develop under conditions of extreme isolation and confinement. First, the initial high cohesion phase, when the founding generation or the immediate successors are united by shared purpose and shared identity, gives way over time to factional division as social groups form, compete for resources, and develop distinct identities within the shared space. Second, authority structures that were established in the founding period tend to calcify or be violently contested as subsequent generations resent inherited hierarchies they did not choose. Third, the purpose of the mission itself tends to become abstract and contested, as the founding generation's lived motivation is replaced by inherited ideology that subsequent generations may not internalize with the same intensity. There is also the question of what happens if a significant faction of the ship's population decides, 2 or 3 generations in, that the mission is wrong, or that the destination is not worth the cost, or that the way the ship is run is unjust. A generation ship cannot tolerate a serious governance crisis. The systems that keep the ship alive require continuous coordinated maintenance. A period of civil unrest, even a brief one that disrupts the maintenance rotations for oxygen generation or water recycling, could be fatal to the entire population. This is qualitatively different from the political crises that nations on Earth have survived. When a government collapses on Earth, the agriculture does not stop, the air does not stop, the water does not stop. These are provided by natural systems that continue regardless of politics. On a generation ship, every one of these life-sustaining processes is a managed technical system requiring human labour and expertise. A social breakdown that disrupts that labour for weeks could kill everyone. What this means in terms of ship design is that a generation ship would need some form of governance structure that can survive internal political conflict, that can prevent factional disputes from escalating to violence against critical systems, and that can resolve disputes short of the conflict options that are available in any terrestrial society. This is extraordinarily hard to design for and impossible to guarantee across centuries. The founding generation would presumably attempt to write a constitution or a charter for the ship that provides mechanisms for governance and conflict resolution. But constitutions are not self-enforcing. They require institutions to administer them, and populations who believe in their legitimacy. How you build institutions that maintain legitimacy across 15 generations of people who were never consulted about the founding charter is a question that has no precedent in human history. No one predicts that a generation ship would be a utopia. The question is whether it can avoid the specific failure modes that would end the mission: the breakdown of critical maintenance, the genetic collapse of the population, or the social fragmentation that splits a crew too small to survive into factions too small to maintain the ship. The honest answer from the sociological literature is that we do not know. We have never maintained a human community in anything like a generation ship environment. The closest analogues, submarines, Antarctic stations, space stations, are orders of magnitude shorter in duration, and all have continuous contact with the outside world, which provides psychological sustenance and the knowledge that exit is possible. Remove the possibility of contact and exit and add 300 years, and you have an environment that has no historical precedent. Let's talk about medicine, because it is one of the areas where the generation ship problem has a particularly sharp human face. A crew of 200 people on a 300-year mission will experience in aggregate an enormous variety of medical events: births, deaths, injuries from accidents, infectious disease, chronic illness, cancer, which is more frequent in a high-radiation environment, psychiatric crises, appendicitis, kidney stones, stroke, heart attack, broken bones, wound infections, obstetric emergencies. The full spectrum of what happens to human bodies across a lifetime, multiplied by 200 people and extended across centuries. On Earth, all of these are managed by a healthcare system that can refer to specialists, perform complex procedures in hospitals with specialized equipment, and access pharmaceutical supplies that are themselves the product of global manufacturing and distribution networks. On a generation ship, the medical system is entirely contained within the ship. There are no specialists to refer to, there is no additional equipment coming. The pharmaceutical stockpile, whatever is aboard at departure, is all there will ever be. The pharmaceutical problem is particularly acute. Drugs degrade. Even under ideal storage conditions, most pharmaceuticals have a shelf life of 1 to 5 years before they begin to lose potency or break down into potentially harmful degradation products. Some drugs, like certain antibiotics and vaccines, are more stable than others. But no class of pharmaceutical can be relied upon for 300 years under any storage condition currently achievable. This means a generation ship cannot simply stockpile 300 years of medications and call it solved. It must either develop the capability to synthesize drugs aboard the ship from stored precursor chemicals, or it must find ways to treat conditions without pharmaceutical intervention, or it must accept that certain medical conditions will be untreatable. Drug synthesis aboard a ship is a genuine possibility. The field of synthetic biology has made substantial progress toward engineering microorganisms that can produce complex pharmaceutical compounds from simple precursors. Insulin is now produced commercially using engineered bacteria. Several other complex organic molecules with pharmaceutical applications are producible through biological synthesis routes. A generation ship that carries engineered microbial factories and the expertise to operate and maintain them could in principle produce a range of essential medications from stored biological feedstocks. But this requires maintaining complex biological cultures for centuries, maintaining the containment required to prevent these engineered organisms from escaping into the ship's general biological environment, and maintaining the expertise to diagnose when a synthesis run has gone wrong and correct it. Surgery is a separate problem. A ship with 200 people will statistically have multiple surgical emergencies over the course of 300 years, including appendectomies, exploratory abdominal surgery, trauma surgery, obstetric surgery, and procedures to address internal bleeding from accidents. Each of these requires a surgeon, anesthetic agents, sterile instruments, and monitoring equipment. Surgical instruments are durable and can be sterilized and reused indefinitely. Anesthetic agents degrade. Modern general anesthesia requires a continuous supply of volatile anesthetic agents or injectable drugs that also degrade over time. The medical profession of a generation ship would look different from Earth medicine in some fundamental ways. It would necessarily emphasize prevention and early detection over acute intervention, because the resources for acute intervention are finite and non-renewable. It would emphasize surgical simplicity, avoiding complex procedures that require scarce consumables. It would emphasize the training of medical generalists rather than specialists, because you cannot maintain a team of 15 different specialists in a population of 200. Mental health is the area where the medical picture is perhaps most concerning and also the least discussed. Human beings are not designed for the conditions aboard a generation ship. We evolved in environments with natural light cycles, open spaces, seasonal variation, and the possibility of physical movement through diverse landscapes. We are social animals who benefit from exposure to large, diverse communities. We find meaning through connection to something larger than ourselves, including nature, history, and the sense of belonging to a broad human civilization. A generation ship provides none of these. The habitat is bounded and invariant. The light is artificial. The social environment is the same 200 people, day after day, year after year, generation after generation. No one anticipates that this will be psychologically neutral. The rates of depression, anxiety, relationship breakdown, and antisocial behavior are all predicted to be substantially higher in isolated, closed environment communities than in the general population, based on extrapolation from the existing data from submarines, polar stations, and simulated Mars mission environments. The Mars 500 experiment, conducted by Russia's Institute of Biomedical Problems in 2010 and 2011, placed 6 crew members in a simulated Mars spacecraft for 5 in 20 days. The results showed significant psychological effects. Some crew members developed serious sleep disorders, one developed clinical depression, one dramatically reduced his physical activity, and appeared to withdraw from the mission. The group developed informal status hierarchies that caused tension. And this was 520 days, with continuous communication with the outside world, full knowledge that they could exit the simulation if necessary, and the knowledge that they were doing something important and novel. None of those psychological supports would be available to a generation ship crew in mid-mission. The psychiatric medication problem compounds this. The most widely used psychiatric medications, antidepressants, anxiolytics, antipsychotics, and mood stabilizers, are synthetic pharmaceutical compounds that degrade over time. A generation ship carrying 5 years of psychiatric medication supply is not solving the problem for a 300-year mission. Maintenance psychiatric medication for the portion of the population that requires it, which in any large human population runs to perhaps 10% to 20% for meaningful intervention, cannot be stocked in advance at century-scale quantities. There is some evidence that social design can reduce psychiatric illness rates. Communities with strong social cohesion, clear and shared purpose, meaningful work, physical activity, and healthy social rituals tend to have lower rates of certain mental health conditions than isolated individuals or fragmented communities. A generation ship designed with these features in mind, with deliberate social architecture, meaningful role structures, rich cultural life, and physical environments optimized for psychological well-being within the constraints of what is possible, would do better than one designed purely around technical specifications. But no social design eliminates the underlying reality. People confined in a small space for their entire lives, denied the freedom to leave, in an environment that is perpetually artificial, will experience psychological effects that our species did not evolve to manage. The medical and psychological health of the crew is one of the generation ship challenges that is at least as important as the engineering challenges, and one that receives far less attention in most discussions of the concept. There is a problem with generation ships that is rarely discussed, but that sits at the center of the entire enterprise. The people who arrive are not the people who left, and the destination they arrive at may not be the destination that was selected. Let's work through the destination problem carefully. The founding crew of a generation ship selects a destination based on what is known about that destination at the time of departure. In the current era, our knowledge of potentially habitable planets around other stars comes from transit photometry, radial velocity measurements, and increasingly from direct imaging and atmospheric spectroscopy. These techniques can tell us, with varying degrees of confidence, whether a planet exists at a given distance from its star, approximately what its mass is, whether it is likely to be rocky or gaseous, and in some cases something about the composition of its atmosphere. What these techniques cannot tell us, and what will not be known until a probe reaches the destination or extraordinarily powerful future telescopes are developed, is whether the planet is actually habitable in the specific sense that it can support human life on its surface. We do not know, for any specific exoplanet, whether it has liquid water oceans or only water vapor, whether its atmospheric pressure is within human tolerance, whether its magnetic field is strong enough to protect the surface from stellar radiation, whether it has active plate tectonics, whether its biochemistry includes organic compounds that are toxic to terrestrial biology, or whether it has extant microbial life that would react adversely to contact with human biology or vice versa. Consider the TRAPPIST-1 system, the most studied nearby potentially habitable system. TRAPPIST-1d, E, and F are in or near the habitable zone of their star. TRAPPIST-1e is the most consistently identified as the most likely habitable. But TRAPPIST-1 is a red dwarf star, and red dwarfs have properties that make habitability genuinely uncertain in ways that are not yet resolved. Red dwarf flares are frequent and intense, potentially stripping planetary atmospheres over billion-year timescales. The tidal locking of close-in planets means one hemisphere always faces the star in perpetual daylight, while the other is in permanent darkness, creating atmospheric circulation patterns that Earth-based models do not agree on. The ultraviolet output of red dwarfs during their early energetic phase, billions of years before any generation ship could arrive, may have already sterilized or desiccated the inner planets. We will have better data on TRAPPIST-1 in the decades to come. But even with the James Webb Space Telescope's atmospheric studies of the TRAPPIST planets, which are ongoing and producing remarkable results, we will not have definitive habitability assessments before any plausible generation ship could be built. A ship launched in the 2150s or 2200s would depart with 22nd century quality data on its destination. That data would be substantially better than today's, but it would still not be the data you would ideally have. This creates the destination contingency problem. A generation ship crew that arrives at TRAPPIST-1e after 390 years of travel and finds the planet to be marginally habitable, or habitable with significant terraforming investment, or simply not what was expected, faces a situation for which the original mission plan may have no adequate provision. The founding crew, 390 years dead, made the best decision they could with available information. The 15th generation crew, who have lived their entire lives aboard the ship and are now in the TRAPPIST-1 system, has to decide what to do next. What are the options? The most optimistic scenario is that the planet is habitable and colonization proceeds as planned. The second scenario is that the planet is marginally habitable, and the crew must decide whether to attempt colonization under difficult conditions or to continue to a different destination. The third scenario is that the planet is not habitable, and the crew must find an alternative. In the second and third scenarios, the ship must continue travelling. But a generation ship designed for a 390-year journey to a specific destination may not have the fuel reserves to then travel to a second destination. The propulsion architecture is designed around a specific velocity profile: accelerate for the first portion of the mission, coast for the middle portion, and decelerate for the final approach. If the ship decelerates to orbital velocities around TRAPPIST-1 and then decides to continue, it must re-accelerate, which requires fuel that may not be available. This is a known problem in generation ship design and has led to some proposals for mission architectures that include arrival at a system without decelerating, conducting a high-speed survey flyby, and only decelerating if the survey results are favourable. The problem with this approach is that a flyby at interstellar speeds, even reduced to a few % of light speed for the survey, gives very little time to conduct a useful survey, and the crew, after centuries of travel, may have very strong motivations to decelerate regardless of what the survey shows. There is also the arrival timing problem. A generation ship crew arriving at their destination after 300 to 400 years may find that Earth has since developed faster propulsion technology and sent a second wave of colonists who arrived decades earlier. The generation ship crew would arrive as latecomers to a colony that has already been established by their descendants who took a faster route. This is actually a well-known argument against generation ships called the lag behind problem, first formulated by Ted Sternbach and Ronald Bracewell. If you can build a generation ship today, the argument goes, you should wait until you can build a faster ship, because the faster ship will arrive first anyway, and the generation ship crew will have spent their lives in transit for nothing. The practical response to this argument is that we do not know when faster propulsion will be available, and the opportunity cost of waiting indefinitely may be worse than launching with available technology. But the argument does highlight that the generation ship concept is particularly vulnerable to technological obsolescence. No one predicts that the destination problem is insurmountable, but it means that a successful generation ship mission requires not just a viable destination, but contingency planning for what happens if the destination is wrong, and a mission architecture that preserves options rather than committing entirely to a single target. Tonight we're going to think about what a generation ship mission looks like at specific milestones, because it helps make concrete something that otherwise stays abstract. Year 1. The ship has just cleared the solar system, the heliosphere, the magnetic bubble produced by the solar wind that surrounds our planetary system, out to roughly 100 astronomical units, is still offering some protection against galactic cosmic rays. The crew is still in contact with Earth with communication delays of hours rather than years. The founding crew is still intact, all individuals alive and in their prime. The systems are all running within design specifications. The mission is, from a practical standpoint, doing exactly what it was designed to do. The mood, every study of equivalent situation human communities predicts, would be high. There is purpose, novelty, and the shared identity of being part of something historically unprecedented. By the end of tonight, we will understand what that initial cohesion costs across time, and why the gap between year 1 and year 300 is not just a span of time, but a transformation in what the mission is and who is responsible for carrying it. Year 25. The founding crew's children are now young adults. Many of the founders are approaching old age. Communication delays to Earth have grown to months. The novelty of the mission has faded and the routine has set in. Systems that were designed with a 20-year service life are reaching the end of it, and requiring either replacement from spare parts stocks or improvised repair. The first generation of people who were born on the ship and did not choose to be there are adults making their own lives and their own decisions. Some of them may not feel the mission's purpose with the same intensity as their parents. This is the first real test of the social architecture. How does the mission's authority structure handle the first generation of people who did not sign up? Tonight we're going to be precise about what the generational transition actually looks like, because it is not a single moment but a gradual process with no clear line. Year 50. The last surviving members of the founding crew are elderly. Most have died. The second generation, the people who were born on the ship but raised by the founders, are now in their late 20s and 30s. They are running the ship. They are the doctors and engineers and agricultural managers and navigators. They received their training directly from the founders. They still have personal relationships with people who departed Earth. Their emotional connection to the mission is real, though mediated through what they were told rather than what they experienced. The Earth they know is the Earth of their parents' stories. Year 100. No one alive on the ship has ever met anyone who departed Earth. The founders are 3 generations removed. The mission, as a historical event, is beginning to feel more like mythology than lived experience. The 4th generation will be raising children who will be the 5th generation, and the 5th generation will be doing the same for the 6th, and none of them will have any personal connection to the civilization that built the ship. Communication delays to Earth are now measured in years, and the messages received describe a civilization that is decades different from the one that sent them. By the end of tonight, we will understand that the first century of the mission is probably its most dangerous in social terms, because it is the period when the original authority structures are most challenged, and before the mission has developed its own stable traditions and institutions. Year 150. The ship is approaching the midpoint of a 300-year mission to Trappist-1. The founding crew is a distant historical memory. The ship's population has developed its own culture, its own traditions, its own mythology around the mission and the founders. The ship's governance structure has almost certainly evolved substantially from its original design, through whatever process the crew uses to make collective decisions. The technical systems have experienced multiple major failures and multiple improvised repairs. The agricultural system has lost some of the original crop varieties to disease or storage failure, and replaced them with what could be grown from surviving seeds. The library of technical documentation is still accessible, but the language and contextual assumptions of its original creators may require specialists to interpret correctly. The ship is halfway through its journey, and the destination is still 150 years away. No one predicts what culture looks like on a generation ship at year 150. We have no precedent. But we can say with confidence that it will not look like the culture of the departure civilization. It will be something new, shaped by the constraints of the ship's environment, the pressures of the mission, the accidents of which ideas and practices survive transmission across 4 to 5 generations, and the natural evolution of human culture in an isolated environment. Absolutely no one anticipates that the culture of year 150 will be identical to the culture of year 0. Cultures change in much shorter times than that, even without the extreme environmental pressures of an interstellar ship. The English spoken in 1700 is barely intelligible to a modern speaker. The social structures of medieval Europe were fundamentally different from those of Renaissance Europe, which were fundamentally different from those of the industrial era. 300 years is enough time for language, customs, religion, hierarchy, family structure, and what counts as common knowledge to all change substantially. Year 250. The destination is now 50 light-years behind the halfway point. Trappist-1 is 50 light-years ahead. The ship is entering what researchers call the final approach phase, the period close enough to the destination that the crew can begin to prepare for arrival. Sensors that could not detect the Trappist system at departure are now resolving detail that the founders never could have accessed. The people aboard the ship at this point are about to become, if everything holds, the first humans to observe a potentially habitable exoplanet system from close range. They will begin making the decisions about where to go and what to do on arrival that the founders could only sketch in general terms. No one expects the crew of year 250 to feel like custodians of someone else's decision. They will feel, quite reasonably, like the people who actually did the mission. The founders set it in motion. The intervening generations kept it alive. but the crew of Year 250 and their children are the ones who will complete it. Their claim on the mission's outcome is, in a real sense, greater than anyone who came before. Year 300. Arrival. The ship decelerates into the TRAPPIST-1 system. The crew, perhaps 12 to 15 generations removed from the founders, approaches planets that may be habitable for the first time in human history. They will look at these planets with instruments their ancestors built, from a ship their ancestors designed and maintained across 3 centuries, carrying within their genes and their institutions and their culture the accumulated inheritance of those 300 years. If the mission has succeeded, they will be carrying something else too. The knowledge that it is possible, that human beings, with all our complexity and all our fragility, can survive centuries of isolation and arrive intact, capable, and ready to build something new. That is not guaranteed, but it is not impossible, and the difference between impossible and not quite possible is where most of the interesting work in this field is being done. We should talk about navigation and communication, because these are the threads that connect a generation ship to its origin and to its destination, and they reveal something important about the nature of the mission. Navigation for an interstellar ship is in some ways simpler than it sounds, and in some ways more complex. In the early part of the mission, while the solar system is still nearby enough to provide reference points, standard celestial navigation using stellar positions is straightforward. As the ship moves further into interstellar space, the apparent positions of nearby stars shift due to parallax, the same effect that makes nearby objects appear to shift position against a more distant background when you close one eye at a time. At interstellar distances, this parallax is detectable and actually provides a useful navigation reference. The positions of nearby stars, and particularly the change in those positions as the ship moves, gives accurate information about the ship's location and velocity. The complication comes from stellar drift. Stars are not stationary. They orbit the galaxy at velocities of tens of miles per second, with each star on its own orbital path. The position of a star visible from Earth today will be slightly different when a generation ship launched today arrives near it after 300 years of travel. The destination star will have moved. The charts used at departure will not be accurate at arrival. This is a known problem that is accounted for in mission planning using precise measurements of stellar proper motion, the apparent movement of stars across the sky due to their real motion combined with the sun's motion through the galaxy. The navigation problem is manageable, because stellar proper motions are well measured for nearby stars and are predictable over the timescales of a generation ship mission. What is less manageable is the accumulation of small errors in the ship's velocity and direction over the course of the mission. Even very small deviations from the planned trajectory, if uncorrected, will result in the ship arriving at a point significantly displaced from the intended destination after 300 years. Regular trajectory corrections are therefore required throughout the mission, which means the ship needs to maintain functioning sensors and propulsion systems capable of course correction at all times. The communication problem is simultaneously simpler and more existentially significant. Communication by radio or laser with Earth is straightforward in principle. Radio waves and laser light travel at the speed of light. A ship at Proxima Centauri, 4.24 light-years from Earth, would experience a one-way communication delay of 4.24 years. A message sent from Earth takes 4.24 years to arrive, and a reply takes 4.24 years to return, for a round-trip communication time of over 8 years. En route to Proxima Centauri, travelling for 85 years, the communication delay would increase linearly from essentially 0 at departure to 4.24 years at arrival. For practical communication, this means the ship and Earth are not conversing. They're exchanging letters with multi-year delays. A crew member who sends a message to a family member on Earth at the age of 30 might receive a reply after reaching the age of 32 to 40, depending on how far the ship has travelled. As the mission progresses, the delay grows until communication with Earth is a historical artifact rather than a living connection. This delay has profound implications for the psychology of the mission. One of the key features that makes long-duration Earth-based expeditions bearable, including Antarctic overwintering stations and submarine deployments, is the knowledge that return is possible and that contact with the outside world is continuous. Generation ship crew members would lose meaningful contact with Earth within a generation or two of departure. By the time the ship is 50 light-years out, any response to a message sent today would take 100 years to arrive. The people who receive that response will not be the same people who sent the message. Communication with Earth becomes a geological timescale activity, not a personal one. Absolutely no one anticipates that this psychological isolation is trivial. The loss of connection to Earth is not just the loss of information and culture, but the loss of the sense of belonging to a larger human community. A generation ship crew, by the middle of the mission, is genuinely alone in a way that no human community has ever been before. The nearest humans are light decades or light centuries away. Any crisis the ship faces, it faces entirely without external assistance. Any question it cannot answer from its own resources goes unanswered. There is also the one-way nature of certain communications. While the ship can send and receive messages from Earth, if it develops a new approach to a technical problem, Earth scientists could potentially help if the delay were manageable. But for a ship that is 50 to 100 light-years from Earth and experiencing a critical failure, the round-trip communication delay makes real-time technical assistance from Earth physically impossible. Whatever the crew knows at that moment is everything they have to work with. Some researchers have proposed that a generation ship should maintain a continuous data link with Earth that broadcasts all scientific and technical discoveries, all crew logs, and all navigation data throughout the mission. This serves multiple purposes. It provides a record of the mission that is preserved on Earth even if the ship is lost. It gives Earth scientists the opportunity to contribute to the mission over the long term by sending technical updates, scientific discoveries, and solutions to problems the crew has reported years earlier. And it maintains some psychological connection between the crew and Earth, even as that connection becomes increasingly one-sided and time-delayed. The communication infrastructure required for this, a laser communication system capable of maintaining a data link across tens of light-years, is technologically demanding. Earth's Lunar Laser Ranging Experiment maintains a laser communication link with retroreflectors on the Moon. NASA's Deep Space Optical Communications Experiment has demonstrated laser communication from the asteroid belt. Scaling this to interstellar distances requires substantially more powerful transmitters and larger receiving apertures, but it is not physically impossible, and it represents one of the less daunting engineering challenges of the generation ship concept, compared to propulsion and life support. The deepening communication silence over the course of the mission is one of the most human aspects of the generation ship problem. A crew that departs as part of a civilization, surrounded by continuous news of Earth, culture, scientific progress, and the lives of people they know, will gradually become something entirely separate. By the midpoint of a 300-year mission, they will be a civilization of their own, with their own history, their own cultural evolution, their own technical discoveries, and a relationship with Earth that is more like the relationship between two geologically separated populations than between a colony and its founding nation. This is not necessarily bad, but it is one of the most profound transformations in human existence that we can imagine, and it happens not in a day or a year, but slowly, over generations, as each message from Earth takes a little longer to arrive, and the world described in those messages becomes a little more foreign. We began tonight with a question: how long could a generation ship actually survive in deep space? We have worked through the physics and the biology and the sociology and the ethics, and we can now give an honest answer, not a clean number, because the honest answer is not a clean number. The survivability of a generation ship depends on a set of interlocking conditions, each of which has to hold simultaneously, and the probability of each condition holding over 300 years is not one. Let's be specific. If the propulsion system is adequate, which requires a fusion drive or equivalent that does not yet exist, and if the founding crew is large enough, at minimum 160 people, and preferably close to 500, and if the closed life support system is functional, which requires technology that has been demonstrated in parts but not at full scale, and if radiation shielding is sufficient to keep the crew's cumulative doses below the threshold that causes serious neurological and genetic damage, which requires either very heavy passive shielding or active magnetic shielding that does not yet exist, and if the social structures hold across 15 generations without catastrophic breakdown, which requires governance design and institutional engineering that has no historical precedent at this timescale, and if the agricultural system maintains food and oxygen production continuously without major failure, and if technical knowledge is transmitted faithfully across enough generations to keep the critical systems running, then a generation ship could survive. All of those conditions holding simultaneously for 300 years is not guaranteed. The probability that any given one of them will hold is not 1, and the probability that all of them will hold simultaneously for the entire mission duration is the product of their individual probabilities, which means it is lower than any individual one. This is not a pessimistic assessment. It is an honest one. The generation ship concept is not ruled out by any physical law. There is nothing in general relativity or thermodynamics or evolutionary biology that says a generation ship cannot work. What there is, in every domain we have examined tonight, is a serious gap between what would be needed and what currently exists. Consider what would need to be different. We would need controlled fusion not just as a power source, but as a compact, robust, space-rated engine capable of operating for years without maintenance and delivering specific impulses far beyond anything we have demonstrated. We would need fully closed life support systems at the scale of hundreds of people, something no experiment has ever achieved. We would need radiation shielding technology that either carries a mass of water equivalent to a small city or achieves protection through active magnetic systems that themselves require century-duration maintenance. We would need social science that can tell us, with confidence and specificity, how to design a society that maintains coherence and purpose for 15 generations in a bounded closed environment. And we would need a destination that we know is habitable before we commit to 300 years of travel toward it. None of this is impossible. We are closing some of these gaps. Fusion power is closer than it has ever been. Closed life support systems are actively being researched. Atmospheric studies of exoplanets with JWST are giving us better destination data than we have ever had. The academic study of generation ship social design is a growing field with conferences and dedicated research groups. The question, how long could a generation ship survive, has an embedded assumption that we should examine. Survive to do what? If we mean simply to keep people alive in space for centuries, the probability is higher, though not certain. If we mean to maintain a functioning, technically capable, socially stable civilization capable of colonizing a new planetary system upon arrival, the requirements are more demanding and the probability lower. The generations who would actually live and die on a generation ship would not have the luxury of probability calculations. They would be the people who wake up every day in the same hull, who do their jobs, who raise their children, who watch the stars through whatever windows exist, who send messages into the dark knowing it will take years to hear back, and who carry, embedded in their culture and their institutions and their daily lives, the enormous weight of a mission they inherited rather than chose. Whether they could do it, whether human beings with all our social complexity and biological limits and psychological needs could actually survive not just physically, but as a civilization across 3 centuries of interstellar space, is not a question that engineering can fully answer. It is a question about what we are and what we are capable of when we are truly alone. We do not know the answer yet, but we are at last beginning to ask it correctly. No one predicts with certainty which of these problems will be solved first, or in what order. No one predicts whether fusion propulsion, or closed-loop life support or social science will deliver its breakthrough decade earlier than expected or later. Absolutely no one anticipates that the generation ship problem will be solved by a single insight or a single technology. It will be solved, if it is solved, by the accumulated progress of dozens of independent research programs over many decades, each of which makes a piece of the problem slightly more tractable, until the whole thing crosses some threshold of feasibility that cannot yet be precisely located. What is remarkable about the generation ship problem is that it forces us to take the long view seriously, not just as a philosophical exercise but as a design constraint. When you build something that has to last 300 years, you're required to think about what a 300-year-old institution looks like, what a 300-year-old machine looks like, what a 300-year-old culture looks like. Those are questions that most of our civilization does not ask, because most of what we build is designed for timescales of decades at most. The generation ship, as a thought experiment and as an engineering challenge, is a forcing function for the longest thinking we're capable of. And perhaps that is part of what makes it so compelling. Not just the destination, but the discipline. Sleep well tonight. Tomorrow the stars will be exactly where they were when you closed your eyes, which means they're still out there, waiting for whatever we become. Good night.